Regression analysis is a great tool to understand the relationship between a variable and a response to that variable. So for example, if you're baking cookies in an oven, your oven temperature as well as the length of time you bake it is going to affect how brown those cookies get. And so if you really wanted to, you could make a equation to describe that relationship. And this is what regression analysis does. In this video lecture, we'll talk about the two common model types for looking at data, and then we'll differentiate between different regression models. We'll also cover the limitations of regression analysis. Since this is an introductory video, we're not going to go into a lot of details about how to do a regression analysis, but there will be videos later on that describe how exactly to characterize a regression and then look at quantitative ways to look at how well that particular model you've generated fits your data. The two main ways to model data are using mechanistic models and empirical models. Mechanistic models are based on things we know about physical properties, chemical properties, engineering. So these are relationships like F equals ma. So your force is your mass times your acceleration. So we go from a quantum mechanics level up to a molecular level, then up to a mesoscale level, so looking at microstructure, and then we can develop a model based on what we know about this. So this is based on the actual properties of whatever you're looking at. An empirical model is based on data you've collected. So it doesn't necessarily have anything to do with the properties, and it can't necessarily be extended past whatever you're looking at, past your particular data set. But it is a really great tool when you don't know enough to make a mechanistic model, and in fact it can get you enough data sometimes that you can start building that mechanistic model. So each of these models have advantages and disadvantages, and depending on the data you collect and the results you want to see, what you want to understand, you'll pick one versus another. We'll only talk about empirical models in this class. If you want to understand more about mechanistic models, that requires heavy knowledge of the particular thing you're studying. So knowledge of physics or chemistry or something like that. Empirical models can be used for whatever data set you have. And the most common empirical model is a linear regression model. There are several types of these. There's simple linear regression, which is basically y equals mx plus b. So here your betas, your coefficients, here's your intercept, here's your slope. This epsilon is an error term, and that's because you are going to have error when you collect your data, because it is empirical data. It depends on your observations, and there's always error associated with observations. So that's why we put this error term in. You can have a multiple linear regression where you have multiple variables and betas to accompany that. So you can have as many variables you want in there, and then you still have your error term, and that's describing your response, y. You can have a polynomial regression, so you can have a squared term in your variable. You can have many other types of regression here. You can throw in natural logs, you can use a power function, but these are still linear regressions. And the reason they're linear, even though we have this squared term here in our variable, is because all of your betas are linear. So there's no squared terms on your betas, there's no powers of any kind, no natural logs, nothing like that. As long as your parameters, your betas, are linear, that is a linear regression, regardless of what your variable is doing. So make sure that you have that straight. Linear regression refers to the betas, not the variables. And the whole point of doing a regression is to describe your response. Now these formulas look pretty ugly. Don't worry, in this course we're not going to be calculating any of these parameters by hand. We'll use Excel or QI macros or another program to do that for us. But it's important to understand how these models work so that when we get a response, we understand the limitations of the model and what the model can and can't do for us. When you're picking a model, an empirical model, the first thing you want to do is plot your data. So that's our orange diamonds on this graph right here. You're going to perform some kind of regression analysis to fit a trend line to your data. That's that black line right there. And then you want to check the fit of that particular model for your data. So does it appropriately describe the variation in your data, or are your data just kind of all over the place on the graph and the line seems to be haphazardly drawn through it? There's several different ways to check the fit, and some are quantitative, so you can actually get a number to check it. We'll go through those in the next couple of lecture videos. But right now, let's talk about the limitations of empirical models, because they can't do everything. So the more data you collect, the better model you're going to have. More data strengthens your model. 2 points make a line. So regardless of whatever relationship those 2 points have to each other, you're going to get a straight line between them. If you have 4 points, let's say, that's better, but you can still probably fit a straight line to them and have a reasonable fit, even if that isn't the true relationship between those points. You have more fit error on the ends of your data, and what that means is, if we go back to this graph, in the middle of your data set, so right here, you're probably going to have a pretty good fit. Where the fit starts to vary is the ends. And that's because the regression is comparing one point to another. And when you get to the end, you don't have another point after your end point to compare to your last point. So regression models tend to fit a little bit better in the middle and a little bit worse on the ends. And that means that your model is better for interpolation, not extrapolation. So extrapolation is going beyond your data set that you've collected. Interpolation is going for a point that you didn't specifically measure, but is between 2 points that you have measured. So keep that in mind when you're using your model to make predictions, that if you are going for something that's very far outside of your data set, you could be way off in your interpolation. This is similar to the whole gas will be $12 a gallon in a year argument. Maybe if the model you use to calculate the increase in gas prices is correct all the way out to $12 a gallon, but in reality there's a lot of other factors that are going to affect that model, and you'll probably see a stabilization of gas prices at some dollar amount that's less than 12, at least in the US. Another thing with empirical models is that if you have outliers and non-random error, that can impact your results. An outlier is a point that is way far off of your bulk data set. That will pull your line one way or another towards the outlier. Non-random error is talking about error at a specific point in your measurement that is either significantly higher or significantly lower, or somehow otherwise related to itself. Random error is not related, it just sort of happens as a function of the measurement. Let's say you're measuring viscosity and you know for a fact that you have much higher error at lower shear rates. So that error at the lower shear rates is going to pull your model off. Also, if we look at nonlinear relationships between our data and our our variable and our response, and we're trying to make a linear fit, we may not be able to fit very well. So if we're using a model that doesn't properly describe the relationship of our data, then we may get our model to fit, but it probably will not at all be accurate outside of our particular data set, and it probably isn't the best model that we could use to describe this relationship. So you want to make sure that you have a good idea of what sort of relationship your variable and response has to each other when you're trying to fit a model to the data. And finally, when you're looking at these empirical models, you'll be able to develop one for your data, and it may be an excellent fit and everything looks great, but that doesn't necessarily relate to what's really going on physically or chemically or anything else. So you have this model, but what does it actually physically mean? Think about that when you're developing your model and see if you can develop these relationships between the model you're getting, the numbers, and what's really happening in your system. Because that's one of the main reasons we make these models, is so we can figure out what's going on. But if we can't map our model to reality, then we have an issue, and we may need to go back and reevaluate how we're fitting this data. So in general, empirical models are great when you have a data set and you don't know enough to make fundamental judgments about your data. But you have to be careful and make sure you're working within the limitations of these models so that they can give you an accurate representation of what is happening.